Welcome. So we will continue with the assignment number 5 today. So question number 1 is a nozzle receives zero point 0.1 kg per second of steam at 1 megapascal and 400 degrees Celsius with negligible kinetic energy. ठीक है. So mass flow rate they have given as m dot in is equal to 0.1 kg per second. Okay. And pressure. So suppose let's call inlet state as 1. So mass which is coming in we will denote by m dot 1, that is mass flow rate. Pressure at state 1 is nothing but 1 megapascal. Okay, and temperature at state 1 is 400 degrees Celsius. And negligible kinetic energy means V1 is 0. Means V1 square will be 0, that is m dot V1 square by 2 is equal to 0. Since m dot is not 0, so V1 square is equal to 0, which means V1 will be equal to 0. Okay, so this is our inlet state. And once we will look at means at a given pressure, we will find that the temperature here is greater than the saturated temperature at 1 megapascal. Okay, so this state is nothing but a superheated vapor state. So our state 1 is superheated vapor state. Okay, then next part is the exit is at 500 kPa and 350 degrees Celsius. So 2 is suppose mass flow rate at exit is m dot 2 and pressure is nothing but 500 kPa. Temperature is nothing but 350 degrees Celsius. Okay, and one more thing, flow is adiabatic. Adiabatic means heat transfer rate is 0. Okay, and since nothing is mentioned about the work, so we will also assume that work transfer is also equal to 0. Okay, so once we will look at look from the table of look from the steam table, we will find that at this given pressure. So let me check. So it is also at a superheated state, because at this given pressure P2, we will find that the temperature, saturated temperature will be less than this. Means this temperature is greater than the saturated temperature. So which means that it is at superheated state. Okay. So what we will do is we will apply okay. So we will apply yes. So since means nothing is mentioned about unsteadiness, so we will assume that it is a steady state steady flow process. So assuming steady state steady flow process, so what will happen that m dot in minus summation of all m dot in minus summation of all m dot out is equal to dou m by dou t control volume. Okay, since it is a we are assuming it has steady state steady flow process, so it will become 0, and summation of m dot in is equal to summation of m dot out. Okay, so here only means since it is a nozzle, so only one flow is there, one inflow is there, which is nothing but m dot 1, and which will be equal to m dot 2, which is exit. So here m dot 2 is nothing but equal to m dot 1 from mass balance. Then second thing is energy balance. Okay, so what we have, E dot in minus E dot out is equal to dE by dt CV. I am doing this in the question number 1, and I will not do this again means in throughout this assignment. Okay. So this will be 0 since it is a steady state steady flow process. So which means E dot in minus E dot in is equal to E dot out, and it should be known to you that the what are the component of this energy for the open flow means for open system. So it is nothing but some work will be coming in, some work will be or some heat transfer must be taking place, and also the energy which is carried by flow, which is nothing but is m dot in, which is here m dot 1, or m dot in for generalization, and it is nothing but h1 plus v1 square by 2000 plus gz by 1000. Okay, so same thing here, that is w dot out plus q dot out plus m dot h2 plus v2 square by 2000 plus gz by 1000. Okay, so one thing to note, why I have written here 2000 and 1000, because h1 will be always given in kilojoule per kg. Okay, and v1 square will be always in meter per second. Okay, so whenever you are using h1 in kilojoule per kg and v1 in meter per second square, sorry, in meter per second, and z in, what we say, z in meter. Okay, then you have to divide by the factor of 1000. Okay, so as to get this quantity in kilojoule per kg. Okay, so that's the catch. If you are putting velocity in meter per second, then only you have to do this. Means if you want this in kilojoule per kg, otherwise if you are substituting h1 in joule per kg, then there is no problem. You can drop this 1000 from here. Okay, you can just write v1 square by 2, but just to avoid complexities, we will always use this form. So that, let me write it here, that is h1 in kilojoule per kg, v1 in meter per second, and z in meter. Okay, so this thing you have to keep in your mind throughout this. Whenever you will apply the energy equation for open system, this thing you have to follow. So since no work is taking place, neither we are giving input to the system, nor we are taking any output from the system. Similarly, about the heat transfer, they have mentioned it as a adiabatic process. What will happen here? They have mentioned that inlet kinetic energy is negligible, means V1 will be 0, and this is also 0. Then V2, they have not mentioned anything about V2, and we need to calculate V2. Okay, and GZ is also neglected because nothing is given about Z. Okay, so we are left with m dot in is nothing but m dot 1, and it is h1 is equal to m dot out is also m dot n. From mass balance, it is h2 plus v2 square by 2000. I hope you got till this point. Then it's just a manipulation, algebraic manipulation. Thermodynamics is over. So what we'll get, this will cancel from both the sides. So we will have h1 minus h2 times 2000 under root, which is nothing but equal to v2. Okay, so what we have with us, we know p1 t1, and we know that it is in saturated superheated vapor state. So we will get h1 from the table. Similarly, for here we will get h2 from the table. Since h1 and h2 is known to us, so h1 is known, h2 is known, so we can get v2. Accepted answer is D. So D will be the correct answer for this. Once you will put the values for h1 and h2, you will get this answer. Okay. One thing, be careful about unit. Then second part is find the nozzle exit area. Okay. So for exit area, what you means what we know is that mass flow radius can be written as rho AV. Okay. The rho is a density, A is the area, and V is a velocity. Okay. They are asking about exit. So m dot E is equal to rho E, AE, VE. Since they are asking about AE, we can write mass flow rate at exit and entry are same, so just write it as m dot, and it is rho E by VE. How? We have just brought this rho E and VE to this side, and velocity at exit is nothing but V2. Let's be consistent with our notations so as to it is M2 root 2 A2 V2, since it is A2 by root 2 V2. Okay, so we know that density is in kg per meter cube, and 1 by density is in meter cube per kg, which is nothing but equal to specific volume. Okay, so it is m dot v2 by v2. This is specific volume, this is velocity. Okay, since we have calculated exit velocity from above, and from the steam table we can get value of mu2. Okay, at this point of time you should know how to calculate value from the steam table. Otherwise, means in gate exam they will give you some table of different values. You have to select value from them. In order to confuse you, they can give you, it may be possible that they will give you both superheated as well as saturated property table. So you must be thorough with this property calculations. Okay, means at least identification. So you will get v2 from the table. So once you have v2 with you, then since m dot is known to you, v2 will be known to you, and this is the specific volume is known to you from a property table, and velocity at exit you have calculated, so you will get some value. Okay, so here they have mentioned in centimeter square, so mass flow rate is in kg per second. Okay, and this is in meter cube per kg, and it is in meter per second. Okay, so it is per second get cancelled, kg will be cancelled, so it will come out in meter square. Okay, so you have to adjust for the units in order to write it in centimeter square. So means 1 meter is equal to 100 centimeter, I think 100 or 1000, I've forgotten. Okay, whatever it may be, just look at it, or let me check. Yes, I was correct. 1 meter is equal to 100 centimeter. Okay, so just put here, so that you will get your answer in centimeter square. Okay, so this will be the correct answer. I hope you got the procedure how to arrive at this. Just look at the property tables, substitute the value, and cross check the answers. You are getting it or not, and be careful with the units. Then third question is, diffuser as shown in the figure below has air entering at 100 kPa. Suppose this is our state 1. So pressure at state 1 is 100 kPa. Okay, and temperature is also given 300 Kelvin. Velocity is given 200 meter per second, and inlet cross section area is 100 mm square. Okay, be careful with the units. And exit area is 860 mm square. So 1 mm square is equal to, means put it in 1 mm is 10 to the power minus 3 meter. So you will get 860 into 10 to the power minus 6 meter square after conversion. And exit velocity is 20 meter per second. And writing is coming so bad. Okay, then what they have asked, they asked us to determine the exit pressure of air, that is P2. Okay, so we know that, again assuming steady state steady flow process. Why? Because they haven't given anything that anything is changing, and unless otherwise stated, we will assume steady state steady flow process. Okay, so what we have is summation m dot n is equal to summation m dot out. Since only one inlet one outlet, so m1 m dot 1 is equal to m dot 2, and m can be written as rho 1 a1 v1, rho 2 a2 v2, and since it is a air can be assumed as an ideal gas. Okay, so applying ideal gas equation, we know that PV is equal to mRT, that is P is equal to rho RT, rho is equal to P by RT. Is P by RT1 A1 V1 equal to P2 by R T2 P2 V2. What we have with us is we will get solving this. They have asked us exit pressure, that is P2. So P2 will be equal to P1 times T2 by T1. Okay. The A1 V1 by A2 V2. Okay. So we know A1, we know A2, we know V1, we know V2. And similarly T1 is known to us, only T2 is not known to us. So we will use our second equation, that is energy balance equation, that is E dot in is equal to E dot out for steady state steady flow process. Since no, did they mention anything about heat? Nothing is mentioned about heat transfer as well as work transfer. So we will assume both heat transfer as well as work transfer is 0. Okay. So say W net, whatever, no need to write. Or let me just write. That is Wn plus Qn m dot in H1 plus P1 square by 2000 plus Gz1 by 1000 to W out, Q out. Start with the complete equation so as to avoid making any mistakes. Okay, it will not take much time to jot down this equation. V2 square by 2000, then Gz by 1000. Okay, nothing is mentioned about this. Similarly, this, so 0. And potential energy changes are also negligible because they haven't given any information related to this. And what about velocity? Velocity at both entry and exit they have provided. And also one more thing, since from what we can say, from mass balance we got m dot in and m dot out are equal, and since both the terms of the sides have cancelled, so this will also get cancelled. We have with us h1 plus v1 square by 2000 plus is equal to h2 plus v2 square by 2000. Okay, now since we can assume Cp for air as 1.005, assuming air as a calorifically perfect gas, because they haven't provided any table or any other information to get H1. So we'll calculate H as Cpt. Okay, so H1 will be Cp times T1 plus V1 square by 2000 is equal to H2 plus V2 square by 2000. Okay, so Cpt2. Okay, so what we want, we need to calculate pressure, and for that we need temperature T2. Okay, so from this equation, write it here. Okay, so T2 T2 will be equal to V2 square, V1 square minus V2 square by 2000 1 by Cp plus T1. So V1 is known to us, V2 is known to us, and T1 is known to us. Cp we have assumed 1.005 kilojoule per kg Kelvin. Okay, everything is known to us for left hand side. So we can calculate T2, and once T2 is known to us, we will put it here and get the value for P2. So B will be the correct answer. You will not get exact answer since we have assumed H as CPT, and in their solution they have assumed means the value of H from the air tables. Okay, so you will get a slight difference in the answer once you will calculate this value. Okay, but understanding the procedure is important than this final value. But in order to practice, you have to calculate final values. Okay. Then coming to the next question. Okay, so R134A is throttled. So what is throttling? It is a kind of a process uh, in which enthalpy at the initial state and enthalpy at the final state remains same, and we get a drop in a temperature due to a drop in pressure. Okay, so that's how this throttling process works. Then what we have is we have T1 as 25 degrees Celsius and P1 as 750 kPa. Negligible kinetic energy means V1 is nearly equal to 0. Okay, then P2 is 165 kPa. So see how much drop in pressure we are getting through this process. Okay, and assume the velocity remains constant means V2 will also be equal to 0. Okay, so and since they have nothing mentioned nothing about the potential energy, so we will also assume Z1 is nearly equal to Z2. Okay, then the exit temperature of the refrigerant. So mass flow rate will obviously remain same, and m dot n is equal to m dot out is equal to m dot. Assuming it as a steady state, steady flow process, and applying mass balance. Similarly, applying energy balance, what we get? No work is done, that is Wn, but still let me write. Okay, h1 plus v1 square by 2000 plus gz by 1000 w out plus q out plus m dot h2 plus v2 . Okay, so no work, no heat, because throttling process is adiabatic process, and no work transfer takes place during that process. And also they have mentioned that negligible kinetic energy means v1 is 0, and also velocity remains constant, so v1 will be equal to v2, and nothing mentioned about potential energy, so we'll assume it as 0. So we will arrive at h1 will be equal to h2, since mass flow rate is also same at entry and exit. So from energy equation, what we got? H1 is equal to H2. So once we will go through this R1348 table, what we will find out that at this temperature, let me check. Okay. So one more thing, means unless otherwise mentioned, we will assume that entry to the throttling process is as saturated vapor. Okay. So at state 1, we will get our specific volume as we need to know the enthalpy. So just straight away come to the enthalpy. That is H1 is nothing but HF at 25 degrees Celsius. So it will be equal to 234.59 kilojoule per kg. Okay. And it will be equal to H2. Okay, 234.59 kilojoule per kg. And okay, so what they have asked means at state 1 we have got enthalpy from this property. Okay, and at state 2 pressure is known to us and enthalpy is known to us. And when we will look at the table, at this pressure, we will find that this enthalpy value lies between saturated liquid and saturated vapor state. Okay, so we are in a wet vapor region. So means T2 will be T sat saturation temperature at this pressure, and its value is nothing but equal to T. Then the ratio of exit pipe diameter to that of inlet pipe diameter. Also, we have m dot n is equal to m dot out. Okay, from mass balance. So we have rho 1 A1 V1 is equal to rho 2 A2 V2. Okay, so since they have given that velocity at inlet and velocity at outlet remains same, means they have mentioned kinetic energy is negligible, means velocity is nearly equal to zero, means not exactly equal to zero, nearly equal to zero. Okay, so rho 1 A1 equal to rho 2 A2 because velocity at inlet and exit is same. They have mentioned above. Then what we will get exit and inlet they are asking. So A2 by A1 is equal to O1 by root 2. And in terms of specific volume, we can write as mu2 by mu1. Okay, so A2 by A1, or straight away get to this point. D2 by D1 whole square, because pipe and they mention circular pipe. Okay, they haven't mentioned about circular or anything, but we will still assume circular because nothing is given. Lot of assumptions are made in this question, but in your exam they will give you all the description and assumptions required. Okay, so no worries. Mu2 by mu1. So how you will get mu1? So from T1 and P1, mu V1 will be equal to Vf at this properties. Okay, and for mu2, what we will do, since H2 is known to us and we know that it lies in a wet vapor region, so you will calculate property that is Hf x times Hfg. Okay, so they are. Uh, hmm. So okay. Hmm. So from here you will get what you will get quality. Okay, so once you get the quality, mu2 will be known to one, that is Vf plus x times Vfg. So V2 is known to us, V1 is known to us. So you will straight away calculate this ratio of V2 by V1, and once V2 by V1 is known to us, take a square root of it. Straight away we will get answer. And one more point I have mentioned here that entry is assumed as saturated vapor, but it is not saturated vapor. They have got this answer by saturated liquid, assuming it as saturated liquid. Okay, so you have to assume entry to the throttling process as saturated liquid unless otherwise mentioned. Okay, so that's what you need to keep in mind, and sorry for this mistake. Then next question. Question number 6, that is a small expander, a turbine with a heat transfer. Okay, small device is given which has this much of working fluid. Working fluid is helium, and mass flow rate they are given as 0.05 kg per second. Entering, that is pressure, entering pressure is 100 kPa. T1 is 550 Kelvin, and leaving at 250 kPa. T2 is 300 Kelvin, power output, that is W out, is 55 kilowatt. We have to neglect the kinetic and potential energy changes straight away given. The rate of heat transfer to the turbine we need to calculate. Okay. So what we will do is, since from mass balance and for steady state steady flow process, we know that m dot in is equal to m dot out is equal to m dot. Okay. So it is known to us. And from energy equation, we have E dot in is equal to E dot out. So expanding it, we'll get W dot in plus Q dot in plus M dot okay, H1 plus V1 square by 2000 plus GZ1 by 1000 is equal to W dot out plus Q out plus M dot H2 plus V2 square by 2000 plus GZ2 by 1000. Okay, so work input is 0 because nothing is mentioned about it. And since they haven't mentioned it is coming in or it is leaving the expander, so we will talk about net heat transfer. What we'll do is, and also the changes in kinetic and potential energy is 0. That is V1 minus V2, V1 square minus V2 square will be equal to nearly equal to 0, and GZ1 minus GZ2 will be nearly equal to 0. So we are left with only Q1 minus Q out, okay, is equal to W out plus M dot H2 minus H1. I hope you are clear with this, how we got it. So it is our net heat transfer. Okay. So it is W out plus M dot H2 minus H1. So since W out they have given as 55 kilowatt and M dot is 0.05, and for helium you have to assume some Cp. Okay, sorry, not assume some Cp. You have to calculate Cp, gamma upon gamma minus 1 into R, like this. Yeah. Okay. So gamma for gamma is 1.667 for monoatomic gases because it is helium, and R is nothing but characteristic gas constant, which is universal gas constant divided by molar mass of helium. So after putting all this value, we will get Cp for helium, and once you will get Cp, so it is nothing but Cpt2 minus Cpt1. So it will be 55 plus 0.05 Cp delta T. Okay. So from here you will get answer as A. Okay. So what does this negative sign indicates? Negative sign indicates that means Q out is more than Qn. Okay. Means net heat transfer is taking place out of the system. Okay. So whatever our system is means that expander. So net or we can say control volume to be more precise. So our net heat transfer is out of our system, out of our control volume. Okay, so that's what this negative sign is indicating. Then next question. Mass flow rate of steam into the steam turbine is 1.5 kg per second. Okay, mass flow rate they have given as 1.5 kg per second. Also the heat transfer from the turbine, that is heat transfer from the turbine, so it is Q dot out 8.5 kilowatt. Power output of the turbine they are asking, that is W dot out they are asking, and all these values they have given. So at inlet condition we have velocity v1 equal to this, z1 equal to this. Just put the value, get the answer question. And at exit condition at 100 kPa V1 is equal to this, Z1 equal to this. Okay. So from steam table, when you will look at this condition, you will find out that at a given pressure, means at 2 megapascal, the temperature will be, means the saturated temperature will be something, say Tsat, and that Tsat will come out less than this 350 degree Celsius. Means inlet condition is superheated vapor. Okay. And at exit condition, they have mentioned quality as 100%, means it is saturated vapor. Okay. So you have this, then from steam table you will calculate H1 and here H2, and H2 will be equal to Hg. Okay. Then simple mass balance is nothing but m dot in, m dot out, which will be equal to m dot, and energy balance is E dot in, E dot out, W dot in plus Q dot in plus m dot H1 plus V1 square by 2000 GZ1 by 1000 m dot H2 GZ2 by 1000 plus V2 square by 2000 plus W dot out plus Q dot out. So W dot in is 0 and Q dot in is also 0, and only W dot out we need to calculate, and Q dot out is given to us. Okay. H1 is known to us from table, H2 is known to us from H2 is equal to Hg, which is also from the table at 100 kPa. Okay. V1, GZ1, everything is known to us. Be careful about the unit, and finally we'll get your answer. That is D. Okay. Solve it. Just substitution of value, nothing much. Then question number 8. An air compressor takes in air at 100 kPa, 17 degrees Celsius, and delivers it at 1 MPa, 600 Kelvin to a constant pressure pool. Okay, so at state 1, 100 kPa, T1 is 17 degrees Celsius to 73, to 90 Kelvin. Then it delivers it at P2 is 1 MPa, T2 is 600 Kelvin. Here pressure remain constant because they are mentioned to a constant pressure cooler in which air exits at 300 Kelvin. T3 is given as 300 Kelvin. Specific heat transfer in the cooler. Okay. So for cooler they are asking specific heat transfer. That is Q dot cool. So what we'll do is, since m dot in, m dot 1 is equal to m dot 2 and m dot 2 is equal to m dot 3, because steady state, steady flow process. So mass flow rate will not change throughout the process, only single inlet and single outlet. So what we have, applying energy equation at between 2 and 3, that is assuming this as our control volume. What we will have, say E2 is equal to E3 or E dot 2 is equal to E dot 3. Then no, let me write it here. W2, W dot 2, Q dot 2. This will be correct way. Wn plus Qn plus m dot H1 plus V1 square by 2000 plus GZ by 1000, W dot out, Q out, m dot H2 V2 square by 1000 and GZ 1000. Okay, so no work is done in this constant pressure, whatever it is, constant pressure cooler. Okay, just heat is transferred, so that to reduce temperature from state 2 to state 3. Okay, to Q out is taking place, Q in is 0. What we have, and also changes in velocity and potential energy will be negligible. These are not individually 0, but the changes in them is 0. Okay. So don't get confused with that. V1 and V2 are not individually 0. The changes in kinetic energy between state 2 and 3 is 0. And same with the potential energy. What we have is Q out equal to m dot h1 minus h2. So m dot, I think they have given m dot. No. Okay. There is no need of m dot. Let's say it is Q dot out. Then Q dot out, or take m dot to left hand side, you will get Q dot out by m dot as h1 minus h2, which will be Q. It is in specific sense Q cool. It is h1 minus h2. So for air we can write Cp T1 minus T2. Oh sorry, here it is, I messed up. T between state 2 and 3 we are writing now. So it will be 2, will be 3. So it is 2 minus 3. 2 minus 3. So Cp for air is nothing but 1.005. T2 is 600. It is 300. So 300 point some. Okay, let me check. 300 into 1.005. What mistake did I make? Wait a second. So the correct answer is B. I don't know why they have given A. Okay, because once you will calculate, it will turn out as 301 point something, and it is 306 here because they have used, means the values of H2 and H3 from the tables of air for a given pressure and temperature. That's why they means they have got 306.83 value like this. And if you will use this values, then you will get 301 point something. Okay, so B is the correct answer for this. Sorry, miss. I think in first part they are asking about compressor. Okay, so for second part they have correctly given B as a correct answer. See, okay, means heat transfer in the cooler is 306 point something. Okay, but here they want to ask about compressor. It's a printing mistake. That's why absurd answer was coming. Okay, so same thing we have to do for compressor, nothing new. And this steady state, steady flow processes are very simple. You need to just go with the procedure, that is mass balance and energy balance, and little bit understanding of the physical system, that how it works, so that you will be in a position to apply the equation properly in order to arrive at the final answer. Let me begin with this part also, so that we can surely. What we have is same E1 P2. Here we have work input. Okay, don't worry about this sign and all. input they have given somewhere. Mhm. Okay, let me see what can be done. Hmm. So it is a compressor, and for compressor we know that work is input to the system. Okay. So W in, because this is inlet state, and Q in, nothing is mentioned, we will assume adiabatic. Okay. So straight away we will write 0, and mass transfer, or let me write it in specific sense. Okay. So as to avoid any mess, is H1 plus V1 square by 2000 plus GZ1 by 1000. Nothing is going out. We are assuming adiabatic. M dot H2 plus V2 square by 2000 GZ2 by 1000. Okay. Assuming changes in kinetic and potential energy are negligible. So straight away these terms will vanish. Similarly, there is no work output. H2. So what we are left with is W dot N M dot H1 plus M dot H2. So dividing both sides by M dot, what we will get? We will get specific work. Okay. That is Wn plus H1 is equal to H2. This will be the equation. Once we will divide both sides by M dot. No, what mess they did. Let me calculate. Okay. W dot N H2 minus H1. So H2 is 600, and working fluid is same, Cp 600 minus this 290, 1005. Yes. So 310. It is 310, and once you multiply 310 with 1.005, see, multiplied by 1.005, it will come as 306. Okay, 311 point something, 311 point 0.55. Okay, kilojoule per kg. So no answer is matching this one. So correct answer for this is 311.55 kilojoule per kg. I hope you got this explanation how to do this. It's very simple. Just select your control volume, write the energy equation, eliminate the terms which are not required, uh, assume the things unless otherwise given. Okay, but in most of the cases they will give you, it is NPTEL assignment, that's why they haven't given that much focus, but in gate exam you will be given with most of the assumptions. You need not to assume most of the things from your side, so don't worry too much about that. Then final question is two steady flow. Okay, so this one is also a simple question. Two steady flow of air. So we have two streams, that is M1 here, M dot 1 say, and it is M dot 2. This is our control volume.